This is a joint talk with the dynamical system and ordinary differential equation. And the speaker is Stéphane Nonnenmacher, and he is from the University of Paris-Sud en Orsay, and the title of the talk is Resonance in Hyperbolic Dynamics.
Thank you very much, and let me thank the organizers of this Congress and the program committee for giving me the opportunity to talk here. So I will talk about a series of results. Some of them I contributed to, some of them are from other people, and most of my contribution was done in collaboration with Maciej Zworski from UC Berkeley, so I acknowledge this long-standing collaboration. So it will be about the interplay between classical dynamics and classical hyperbolic dynamics and wave propagation. So this is why on this first slide you see on the right a sketch of wave scattering by obstacles, and on the left this is just a picture I will show later about hyperbolicity. So we will be concerned with waves propagating mostly on Euclidean space in d dimension, and the waves are coming, for instance, from the left here, and they are scattered by obstacles. So they bounce on obstacles, and due to these obstacles, they will be scattered in all directions, okay, with different strength and different amplitudes, depending on the frequency of the incident waves and depending on the angles. But this is, let's say, this corresponds to the physically most interesting situation. I will mostly devote my talk to a transient, another regime where we start from a transient, from an initial wave, okay, which is compactly supported. Let's say here this is u at time 0, this is the wave at time 0, and the waves will be then propagated according to the linear standard wave equation, okay, which is generated by the Laplace operator on the complement of the obstacles. And I assume that the obstacles the complement of the obstacles is connected. Okay, so the waves will find a way to escape. Okay, there's no barrier around it. Okay, so we are interested in long-time propagation. What happens for long time? Okay, if you start from such an initial data, and we want to understand actually how waves are decaying to infinity. Okay, the waves, they will not stay trapped, they will go to infinity, and the question is how fast will they go to infinity, at what rate? And there are different ways to measure this decay to infinity. One way is to compute the local energy, that is, of the waves, the energy of the waves contained in some ball of radius r, which I assume to be surrounding the obstacles. And I will call it the interaction region, okay, this ball. And I want to know how much of energy remains in this ball after time t. We know that the global energy on the whole space is preserved by the wave equation, but the local energy will decay, and we want to understand how fast. Okay. Another interesting measure of this decay, maybe a more precise one, is to take the correlation, so-called correlation between our wave at time t and a given test function, which I will also assume to be compactly supported. Okay. So we want to understand how these two things go to infinity. Go to 0 when time goes to infinity. So how fast is this decay, and how does this decay depend on the shapes of the obstacles? Okay, that's the deal. So because we're interested in large time asymptotics, it will lead us naturally to a spectral problem. Okay, because this is a linear equation. We have an operator, a self-adjoint operator, and naturally we're led to study a spectral problem. So to do this, we consider the resolvent of the Laplacian, okay, of the Dirichlet Laplacian. So since I say already that this Laplacian is self-adjoint, and it has, due to the fact that waves can scatter to infinity, it has continuous spectrum on the positive real axis. So anyway, it means that the resolvent itself, the resolvent operator, will explode if we define it initially for imaginary part of the spectral parameter to be positive. This operator will explode when we reach the real axis. However, if we truncate it by a compactly supported cutoff function, which is somewhat arbitrary, okay, which I call chi, then this operator here, the truncated operator, remains bounded and well-defined when we cross the real axis, and it can be actually meromorphically continued to the whole lower half plane. And in odd dimension, there will only be poles of finite multiplicities, which are called resonances. Okay, this is the definition. This is one way to define these resonances. And somehow these resonances will influence the long-time asymptotics of the wave. Okay, so this is why we will pay attention. We'll be mostly interested in the distribution of these resonances in the lower half plane. So here, for instance, I showed a situation where these resonances have a gap. A gap means that above some line below the real axis, some line imaginary part equal to minus a, there will be only finitely many resonances. And here, on the right and the left, there's no resonance. So in such a situation, which we call the situation of a resonance gap, one hopes, okay, one hope that, at least if you do a naive computation, you hope that the quantities like, for instance, the correlation function I had introduced before, could be expanded, should be expanded according to these resonances, the ones which are above this axis. Okay? So if you do, this can be computed by a contour integral, and the idea is that this contour can be deformed, okay? And when it's deformed, it captures it takes contributions from these few poles, okay? And the residues will give you this type of expression. Okay? So this is the type of fine expression we are interested in the long time limit, with a remainder which might be hopefully exponentially small, depending on the width of this resonance-free strip. Okay, so here in this expression appear the function Vj. The function Vj is called a resonance state, so it appears in the residue of the resolvent at the pole lambda j. It is a resonance state, it is a metastable state. It is not L2, okay, it is not square integrable, but it has some physical content, and it has a lifetime, which is given, according to this expression, the lifetime is given by the inverse of the imaginary part of lambda. Okay, so, of course, the deeper the resonances, the faster they decay. So, the question I had asked before has transformed into the following one. How does the shape of my obstacle influence the distribution of these resonances? Okay. So, here this slide is about going to high frequency. We go to high frequency because the statement I had made, the assumption is that there are no resonances in this strip if you go to large frequencies, here or there. Okay, if lambda goes to plus infinity, real part of lambda is the frequency. I assume that there are no resonances, which means that I need to control what's happening at high frequency. And going to high frequency is the same as going to a semiclassical limit. So I don't know, for those people who attended the Nalinian and Tarman's talk this morning, she was talking about the semiclassical limit. So this is what we want to consider here as well. Notice that if I start from the half wave equation, which is half of the wave equation, by just I can multiply on the right or left by h, okay, and I obtain an equation which looks like a Schrödinger, semiclassical Schrödinger equation, when this parameter would be a Mach Planck's constant. And going to high lambda, high frequency regime corresponds to going to the semiclassical regime when this parameter h becomes very small, keeping the energy of this operator, the spectral parameter of this rescaled operator, around 1. Okay? So now we are in the realm of semiclassical analysis, and as was explained this morning, this analysis tells us that the quantum dynamics, the Schrödinger dynamics, can be guided, can be put in correspondence with classical dynamics. And in this situation, classical dynamics is just the geodesic flow or the ray dynamics, the dynamics of rays on this phase space here. And I will focus, because I focused on classical energies 1, it means that I will look at the geodesic flow on the unit cotangent bundle. Okay. So here P is just the classical Hamiltonian, which generates the classical flow. So this correspondence this morning was expressed in terms of the so-called Yegorov theorem. Here I rather use a wave packet to describe this correspondence, because they will be more useful for my aims. So I call a wave packet, or minimal uncertainty wave packet, a wave function of this type. Okay, there's, let's say, a compactly supported symbol A here, which is smooth function compactly supported, and I scale it this way, and I multiply by this exponential phase here, right? By this phase. So this represents in quantum dynamics, in semiclassical analysis, this represents a wave packet which is localized near the point x0, and which is localized in momentum space, or Fourier space, which is localized around momentum psi0. Okay, psi is the coordinate in the fiber of the phase space, and x is the coordinate in space. Okay? So this is a minimal uncertainty wave packet. This is what approaches most precisely a point in classical mechanics, point and velocity. And what happens if you start from such a wave packet? So here I describe it by this sort of rays. Okay, here the bars represent the equiphase planes. Okay, so they are at distance h, and the whole thing has a width square root of h. And here I describe the same object, but in phase space, x and psi. So when you run the dynamics, the quantum dynamics, this object, this wave packet, will follow the classical rays, the classical geodesics. Okay? So the center of the wave packet will follow the classical geodesic. It will bounce on the obstacle, okay, and bounce again. So in phase space, it will follow, the center will follow the geodesic, okay, in phase space. And at the same time, so we say that, this is why we say that quantum dynamics follows classical dynamics, because notice that this is microscopic, this has a width square root h, and this is still microscopic. So this is still a wave packet which follows microscopically a classical trajectory. But now we say that this state is microlocalized. Okay, this is the term for microlocal analysis. Microlocalized means localized in space and momentum, okay, or Fourier space. So when we run it, our space is microlocalized at the image of the initial point, phase space point, through the geodesic flow. And we see something else here. We see that even though the center follows the geodesic flow, the shape, so if we zoom on the wave packet, its shape, in general, its shape is changing. Here it is longer, it is distorted, and it is distorted by the linearization of the flow near this trajectory. Okay, so this linearization is important, and it induces a dispersion of my wave packet. Okay, and this dispersion will be important, because you see that if this trajectory is unstable, is hyperbolic, then along some direction, the wave packet will stretches exponentially fast, okay, along the unstable direction. And this phenomenon will be very important for our aims. Okay, so there is another type of model which can be treated along the same lines. Now it is a true Schrödinger equation with a Schrödinger operator, okay, h squared Laplacian plus v of x. Notice now that this expression, this equation genuinely depends on h. H now is not anymore a toy parameter which I added on the right and left, okay? So it really depends. So this potential will be assumed to be smooth and to be compactly supported. So we are still in a regime of scattering when the waves are scattered by the potential. And now we can analyze as well the evolution of wave packets, and the wave packet will now follow not the geodesic flow, but the Hamiltonian flow generated by this Hamilton function. Okay? And this Hamilton function is just the classical symbol of this operator, okay? The semiclassical symbol of this operator. So what we can do in this setting, we fix some energy, okay? And we will look at the resonances near this energy at distance of order h of this energy. And now the resonances are called Zj. They depend non-trivially on h. Okay, they depend on h because the operator depends non-trivially on h. Okay, so this is a setting where our results will apply as well. Okay, but I will rather, for the sake of the exposition, I will rather mostly use the case of hard obstacles because they are easier to present visually what's happening. So now I want to understand the connection between the evolution of the waves corresponding to the classical dynamics. So because we want to understand the long times of the waves, we will have to, and because we are in a semi-classical regime, we will have to understand the long time asymptotics of the classical dynamics. Okay? And so these long time asymptotics means that we are entering in questions of dynamical systems. Okay? What is the long time property of the flow, of the geodesic flow between these obstacles, okay, surrounding geodesic flow, the broken geodesic flow, or the ray flow induced by these obstacles. So what we can see in these pictures is that most trajectories will escape, okay, in finite time. So here escape means that they will come out of this ball. And once they come out of this ball, they never come back, because outside of this ball, the metric is flat and the trajectory never comes back. Okay, so most trajectories will do that. However, they may exist, okay, depending on the shapes of the obstacles, and I will give them several examples. They may exist trapped trajectories, which are trajectories which never come out, never exit this region, this interaction region. And here I just show one of them, which is this periodic geodesic or closed geodesic, which bounces back and forth between the two obstacles. But as you can guess, there are much more trajectories of this type. So this allows me to define the trapped set, the set of trapped trajectories on the unit cotangent bundle, which are the set of points which never exit this region. And the main idea of the whole talk somehow is that the distribution of the resonances which I'm interested in, that is the resonances which are at finite distance from the real axis, which are relevant for wave evolution, it is strongly depending, it should be strongly depend at high frequency on the properties of this trap set, on the geometric and dynamical properties of this trap set. Okay, this is the main point of, let's say, the stress idea of my talk. Okay, so I will look at several examples. Okay, so I start with a trivial example somehow, the case where there is no such trapped trajectory. Okay, so this is the case, for instance, if our obstacle is strictly convex. Of course, all trajectories, they go away. they cannot be trapped. And in this case, it was shown already some time ago. Okay, this started in the 60s. Okay, and then it was, let's say, improved. But it was it was shown that there is no resonance at distance of order h, or there are finitely many distance at distance of order 1. Okay, and more precisely, the imaginary part of resonances, it is necessarily larger than the logarithm of the real part. Okay, so you see that for any strip of finite width will contain at most finitely many resonances. And in this situation, people could show that the energy, for instance, decays exponentially in odd dimension. The second case is somewhat the opposite case. Okay? It is the situation where not only do I have trapped orbits, but these orbits are stable. Okay? They are not. If I perturb the orbit a bit, it will still stay close to the initial one. Okay? It is elliptic. Okay? So here, this is this type of picture. Okay? Maybe this is an artistic picture, but okay, this is this type of orbit. You can imagine that because the convexity, the boundary here is concave. If you perturb a bit the orbit, it will still remain there. Okay? So in this case, it was shown by these people that one can construct almost eigenstates of the Laplacian, or quasimodes of the Laplacian, which are localized near this orbit. Okay? And these quasimodes are very good. So quasimodes mean approximate eigenstates. And these approximate eigenstates become better and better if I go to high frequency, because I can really construct wave packets which are very close, which remain very close from this orbit. And because of the stability of the orbit, the wave packet does not disperse. Okay? Maybe it can be turned a bit, but it cannot stretch, it does not stretch. And therefore, one can construct so-called Gaussian beams, okay, in the neighborhood of this orbit. And then, once you have this approximate, this quasimode, it is not so hard to show that there is actually, near a quasimode, there is actually a resonance of imaginary part very close to the real axis. Okay. So in this case, we have many. One can prove, these people prove that there are actually many resonances very close to the real axis. So there's no gap, okay, per se. All right, so I will treat now something intermediate, a situation which is intermediate between these two ones, situation when there is one orbit trapped, okay, only one orbit, and this orbit will be assumed to be hyperbolic. This is the case when I have, for instance, two disks. I have scattering by two disks. Okay, they may not be of the same diameter. I put them on the same diameter, but it's not necessary. And it can be. They don't need to be disks, but here it's easier for numerical computations. So in this situation, the trap set is a single hyperbolic orbit, and it has, because of the concavity here or convexity of the boundary, we have dispersion. That is, we have this orbit is unstable. You can imagine that if you perturb a bit this orbit, then a little bit, then the angle, the perturbed orbit will soon escape, and it will escape exponentially fast. So to draw this, let's say more concretely, what one can do is to use reduced dynamics that is only record what is happening when one hits the boundary of this obstacle. So record only the position on the boundary, this S. Okay, S is the position on the boundary starting from here, and the angle or the cosine of the angle, okay, of the incoming ray. So if you do this, this is a reduced phase space. Okay, here this is this S, this parameter on the boundary, and this is the cosine of the angle. And when you hit the first time, you hit a second time, and then you exit. This is recorded by this point rho here. This point here, it maps here, and then it escapes. It does not come back. And if you do computations, you realize that the periodic orbit is given by this point, okay, the point 0, 0, okay, at the center. And this point admits an unstable manifold, this red curve here, and a stable manifold, this blue curve. Okay, so which means that points which starts on this blue curve, they will converge to the orbit in the future, and points which are on this red curve, they will converge to the orbit in the past. Okay, and that's the only ones. All the other ones will escape in the future and in the past. So let's look again at our wave packets. Let's assume that we put a wave packet near this orbit, and along this orbit. Okay, so this is drawn by this circle here. Okay, this wave packet of width square root h, and let's iterate it. So if we iterate it, let's say that we try to represent this wave packet when it hits the boundary here. It starts from being a circle, and then due to the dispersion, to the instability of the flow, it gets stretched along this direction. So this is what I want to feature here. It gets stretched along the unstable direction, okay? And one can compute that it gets stretched at this rate, at the rate given by the Lyapunov exponent of the orbit, e to the minus t nu gamma over 2. So because of the stretching, because the state becomes longer by this length e to the t nu over 2, and its L2 norm remains the same, it has to decay. The L infinity norm has to decay, and the overlap with the initial state has to decay. So this is why we get this decay of the evolved state with the initial state, okay, taken with the initial state. And somehow this feature, okay, this property explains why for this system one can show that there is a resonance gap. Okay, there are no resonances in a strip of width nu over 2. And this nu over 2 is really the same nu. This is really the Lyapunov exponent. So if you do more involved computations, you can show that actually resonances, you can have very precise description of the resonances. They lie on a deformed lattice. Okay. So here we see that there is a connection between the instability of the trapped orbit and resonance gap, the width of a resonance gap. And we would like to see if this is proper to this very simple situation, or if this can be generalized. So the first generalization will be of a chaotic type. So this is why I say that we enter the realm of quantum chaos, okay, because this is a wave propagation of classically chaotic situation. Okay. So this is the situation where we just add a third obstacle. Okay. So let's say we have just 3 obstacles. This 1, 2, 3. So it's not difficult to convince yourself that for this situation, the trap set will be very rich. Okay? It will contain many orbits. Okay? Here I draw, for instance, a few periodic orbits, okay? But there are also many non-periodic orbits. Okay? There are actually infinitely many, uncountably many orbits, okay, in this are trapped. Okay? So here I tried. Okay, I drew this from. I extracted this from some paper, and I think this picture was done by Leon Poon several years ago. It is a sort of identical. It is similar to what was made here, but of course it's more complicated. So it was representing also a reduced phase space situation. So, and you have to make to convince yourself. I'm sorry. Oops. You have to convince yourself that this picture shows here there are stable manifolds in this direction. These are stable manifolds. So these 3 rectangles correspond to the three boundaries of the 3 obstacles. This one, this one, this one. Here this is the S parameter. Here this is the cosinus phi parameter, the angles. Okay, and okay, the different colors correspond to points which escape after a certain time, okay, in certain regions. So the precise definition does not import, but what you have to, outside of these red, blue, and green stripes, what remains are the points which do not escape in the future, so the points which are trapped in the future. So namely the points which converge to remain here forever in the future. And this, you see that this has some fractal structure. And if you go in the past, you will see some similar shapes in the other directions, which correspond to these unstable orbits. Okay, and these will be the points which do not escape in the past. And if you take the intersection of both, you see the yellow points here and here. So the fractal set made of the yellow points, these yellow points are a visualization of the trapped set for this system here. Okay. So it is a fractal set. It is a hyperbolic repeller because the orbits are unstable. And the flow there is axiom A. Okay, it's an axiom A flow. So here I recall briefly what is hyperbolicity. Okay, hyperbolicity means that transversely to one trajectory, there are unstable, here in red, and stable directions in the tangent to the flow. And which means that the points which are along the stable direction, they converge in the future, whereas the points which are in the unstable direction, they converge to the same orbit in the past. And one ingredient, one quantitative measure, is given by this unstable Jacobian, that is, let's say, the ratio of this length to this length here, which depend on time. It is just, it measures the expansion along the unstable direction. So hyperbolicity is one component of chaos, of a chaotic system, but it is not the only one. The second component is complexity, okay, which means complexity here measures the fact that we have infinitely many orbits. Okay. And these orbits can be in this situation, can be actually indexed by following the sequence of bounces. Okay. For instance, the orbit, these triangle orbits, is associated with the sequence 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, etc. But actually, to any such sequence, to any sequence of non-repeating sequence, so of course it cannot be 1, 1 or 2, 2 is forbidden, but apart from these obvious constraints, any sequence is associated to a trapped orbit and a single trapped orbit. So complexity is the second ingredient of a chaotic system of a hyperbolic repeller. So one way to measure the interplay between this complexity and hyperbolicity is to use measures from so-called measures from thermodynamic formalism. This was called thermodynamic formalism. And topological pressures, this topological pressure here is a sort of average over all long orbits. Okay, you sum over long orbits of size between t and t plus 1, and t is large. And you associate a certain weight, which depends on the instability of the orbit. Okay. So you see for a certain parameter s, so you see that for s large, this will be small. Okay. So this is how this pressure depends on the parameter s. So one can show that for this system, for s equals 0, we have just the count of the orbits. Okay, we count long periodic orbits. And because these long periodic orbits, the number grows exponentially, this topological entropy is positive. On the other hand, if you take s equal 1, one can show that the pressure is negative. It represents the classical decay rate, that is the rate of decay of a cloud of particles. If you put a cloud of particles around your obstacles and you let them evolve by the geodesic flow, they will asymptotically, the local mass will asymptotically decay exponentially with this rate. Here, in quantum mechanics, we will be interested on the specific value of the pressure at s equal to 1/2. So this pressure at 1/2 can be either positive or negative, depending on the thinness of the trap set. Okay? So we say the trap set is thin if the pressure is negative, the pressure at 1/2 is negative, otherwise it is thick. Okay? And in 2 dimensions, this thickness can be directly measured by the Hausdorff dimension of the trap set. So first, the result I want to show is that depending on the value of this pressure, if this pressure is negative, so if the trap set is thin, then we have a gap. Okay? And the gap is given at least by the value of this pressure. And we have a gap, and together with the gap, we also have some nice estimates of the resolvent inside this gap. Okay, so that's the main result, which is quite general, which is quite robust. Okay, so the proof, I would not show the full proof, of course, but try to give an idea. We want to show this gap, we have to show that any initial state decays, let's say initial state at high frequency decays faster than this factor e to the t to the pressure. Okay. So any initial state at around frequency lambda can be decomposed into wave packets. So let's start to see what happens to wave packets. Wave packet along the trap set will evolve. This is the initial wave packet. Then it will evolve and it will spread along the unstable direction, and after a logarithmic time, after some logarithmic time, it will exit the ball, the interaction region, okay, because it will have size of order unity, it will exit the ball. Okay? So this is what happens to individual wave packets. However, an initial state is not made of a single wave packet, but it's made of many wave packets. And so even though each of these wave packets will spread out, okay, they can interfere with each other. Okay? They can have interferences, positive or negative interferences, and so this has to be taken into account as well. Okay? So this is why even though each individual wave packet will escape at some point, when you add them up, there could be constructive interferences which make them localize the gain. Okay? So if you sum the contributions, nevertheless, you can show that if the pressure is negative, the dispersion, the individual dispersion beats the interferences. Okay? So this is somehow related to what was in the definition of the pressure. Oops, sorry, no, it doesn't matter. So if the trap set is sufficiently thin, the sum of all these evolved states will still decay, and therefore the local norm, the localized norm of our state will decay exponentially according to this rate given by the topological pressure. Okay. So here, this is this is a sketch of how we can show this decay. So what are the consequences? So this is more for the, let's say, PDE people here, this slide. What you can draw from this resonance gap. You can draw that the local energy decays exponentially, okay, up to some loss. You have a small loss, arbitrary loss in derivatives, but it will decay exponentially. You can show as well that the correlations decay exponentially. Sorry, I have trouble with this machine. Okay, thank you. So the correlations also decay exponentially, and you have well, according to, oh, sorry, there's a mistake. I forgot. There should have been the exponential minus t lambda j. So I don't know how they disappeared. So this was the formula in the first slide, okay, with an estimate here on the remainder. And from there, you can prove all the facts in PDEs, like a local smoothing theorem. Okay. So this is for the Schrödinger equation, for the non-semiclassical Schrödinger equation. If you start from a L2, arbitrarily L2 function, you evolve it by the Schrödinger equation, and you truncate it in some compact part. It is almost all the time, it will be in H1/2. So you have an improvement of the regularity, a certain smoothing of this evolved function through the Schrödinger equation. And from there, you can also show a so-called Strickhart's estimates. Okay. So I will not dwell on this. So there are other models of chaotic scattering. Models, you can replace obstacles by potentials, as I said before. There's also a nice model which is to replace Euclidean space by hyperbolic space and to consider hyperbolic quotients. So hyperbolic surfaces of infinite area, which are obtained by quotienting the Poincaré hyperbolic space by subgroup, a discrete subgroup, certain discrete subgroups. So this gives you a manifold which is like this, okay, which has trapped orbits and non-trapped orbits. So in this situation, there's the resonances are directly connected with the zeros of the Zellberg zeta function. So there's another way to attack the problem, okay, which is very fruitful. Okay. So here, this is the representation in the S plane, okay, and S is connected with lambda in this way. So the spectrum here is given by the line real part of S is equal to 1/2. And it was shown already in the 70s that the resonances are on the left of a line, a certain line, determined by the factor, by delta, a number delta. between 0 and 1. This delta is nothing but the dimension of the limit set. Okay, the limit set here is a set of points which form a fractal set on the boundary, okay, which is directly connected with this group gamma. Okay, so there's a certain fractal dimension which is connected to the fractal dimension of the trap set. And this bound here, which was known so in the 70s, is equivalent with the pressure bound I showed before. So is this optimal? Is this pressure optimal, pressure bound optimal? It is not in general, I think. And for this specific model, okay, the model of the hyperbolic surfaces, there has been improvement. So people have proved that the bound can be, this pressure bound can be improved in general. So this was done first by No, okay, Frederick No, so improved a little bit. So he showed that there's an epsilon gain with respect to this pressure bound. So the pressure bound is equivalent with this delta, this parameter delta bound here. So there's a little extra gap here. And they conjectured with Jacobson that the true asymptotic gap should be given by this line delta over 2, okay, but so far couldn't prove it. And last year there was a really, let's say, breakthrough in the situation for these systems, okay, for these hyperbolic surfaces. This breakthrough was due to Dyatlov, Zal, and then Bourgain, Dyatlov, and Jin and Zhang. So they proved that even for deltas which are close to 1, that is for situations where the trap set is thick, okay, arbitrarily thick, there is a resonance gap. Okay, there is some epsilon with respect to the spectrum, the continuous spectrum. Okay, so this is really somehow, yes. And for this, they use semiclassical methods as opposed to No and co-workers, which were using methods directly related with the zeta function or with classical dynamics. So they use this, and they use also a new fractal, so-called fractal uncertainty principle. Okay, so in a few minutes, which remain, I will present another situation which is interesting, which also features another type of trap set, which is called normally hyperbolic trap set. It is a situation where the set of trapped trajectories is given by a smooth surface, smooth manifold, symplectic submanifold, compact, okay, such that the dynamics is transversely hyperbolic. So the dynamics is not, we don't make any assumption for the flow along this trapped set, but we assume that transversely to it, we have some hyperbolicity, so unstable and stable directions, okay, here. So this is relevant for various systems, like in some chemical reactions, and also for wave propagations in certain black holes, like Kerr black holes. And here, this is like, okay, this picture was drawn from this paper on chemical reactions, for which you had so-called some coordinates for which the dynamics is hyperbolic, and these represent the transverse coordinates, and these represent here the coordinates along this trap set for which the dynamics is regular somehow. So for this situation, we could prove as well, and people have proved as well in higher generality, the presence of a gap, okay? And the gap is also determined, like before, okay, like always, I would say, is also determined by the instability, the rate of instability. And here it's given by the rate of expansion, of growth of this transverse unstable Jacobian, okay? So we proved that there is a gap, and the gap is given exactly by, or at least it's bounded above, by the rate of transverse extension, so the exponential growth rate of the unstable Jacobian of the dynamics transversely to this trap set, independently of the nature of the flow along the trap set. And so this, okay, an idea is, an idea is still, this still resides, this type of result still resides very roughly, of course, on this property that wave packets disperse due to and here they disperse transversely to the trap set. So this point here represents the trap set, and here these two directions represent the transverse unstable and transverse stable directions. So we have the same type of decay as before, and this type of decay is directly connected with this gap. And this result, this type of estimate, had nice applications recently in the control of waves on Kerr-de Sitter black holes. Okay, and finally also on the proof of stability of Kerr-de Sitter black holes by Hinz and Vaschi. Okay, in a few remaining minutes, I will show one other applications of this normally hyperbolic setting, which is somewhat surprising. So this is more addressed now to the dynamical systems people. So here I'm considering an Anosov flow, a contact Anosov flow. Okay, so contact Anosov flow can be, for instance, the flow, the geodesic flow on a manifold of negative curvature, compact Riemannian manifold of negative curvature. Okay. So it is known that this flow is ergodic and mixing, so that the correlations are decaying with time. And it was known since the time of Weyl, I think, that this correlation, the fine decay of these correlations depend on so-called resonances, Weyl-Polycott resonances, which are also discrete points in the lower half plane. And since works of Dolgopiat and Liverani, it was known, I mean, these works show that there is a gap in this Weyl-Polycott resonances spectrum, and this which leads to exponential mixing. And more recently, Masato Tsuji gave an explicit expression of the gap, at least of the asymptotic gap, and he showed that this asymptotic gap was directly connected to the unstable, the transverse unstable, the unstable Jacobian, not transverse, the unstable Jacobian of this Anosov flow. Okay, and therefore one could obtain such expressions for the correlations, okay, assuming the functions are smooth. So this was purely from let's say, classical dynamics people works, and it was realized by Frédéric Faure, and then implemented in papers by Roy and Forchestrand and others, that this situation, the mixing, exponential mixing for Anosov flows, was very similar, and actually not only very similar, but could be really written along the same lines as the decay for scattering waves. So there is really let's say a very similar formalism, or actually a joint formalism could explain the two phenomena. So the idea is to start from the Anosov flow on X and to lift it on the phase space T star X, just lift it to a Hamiltonian flow. Okay, and this is just the Hamiltonian flow generated by this Hamiltonian. Okay, so Xi is the coordinate and the fiber, and V of X is the vector which was generating the flow on the base. Okay, so this is just this is an obvious description of the lifted flow. And the transfer operator, that is the operator which transports functions, density functions, okay, which is just a classical transport, can be exactly written as a quantum propagator, okay, e to the minus I. So this quantum propagator is like a Schrödinger propagator here for this operator, for this quantum operator, which is. So this is just a transport equation, and this is the generator of the transport equation. Okay, so far, this is just a rewriting of the transport equation. And by doing this, we realize that this correlation looks like a quantum correlation. Okay, that has the taste of the quantum correlation, because this is solution of a Schrödinger equation. And by this way, also the resonances of our operator here are directly connected, just proportional to the so-called Weyl-Polycott resonances. Okay. So why does this remark appear here? Because if you look at the dynamics of this flow in phase space, okay, this lifted flow, this flow has the features of the scattering flow. Okay. At each energy, the energy shell is infinite. Okay, it is not bounded but now the infinity is along the fibers. It's not anymore along the x direction, because the x direction is compact. The initial configuration space is compact, but the flow can escape along the fibers in the momentum directions. And it has actually, this flow has a trapped set, which is a normally hyperbolic submanifold, symplectic submanifold. Okay, and if you analyze this normally hyperbolic submanifold, you find that okay, the transverse hyperbolicity is directly connected with the initial hyperbolicity of the Anosov flow. Okay, and therefore, by looking back at our result on the quantum resonance gap, we find that it is exactly equivalent with. We recover the result by Tsuji. Okay, so we put somehow quantum mechanics, if you want, has been implemented in order to obtain a result in classical mechanics, in classical chaotic dynamics. Okay, so I find that this is a nice interplay, a nice, let's say, coming back of quantum to classical. Okay, so I just had a slide of, let's say, describing some other developments. So these are a few themes, a few topics which I did not mention, but which have attracted interest by the people. So it's interesting to count the resonances. Once you go below this gap, when you start to have resonances, you can count them, and the counting leads to interesting fractal Weyl upper bounds. So the number of resonances grows like a power of the frequency number. Okay, but this power is not integer like in the standard Weyl's law, but it is fractional, and it is related with the dimension of the trap set. Okay. So it's interesting also to consider, to investigate the structure, the structure of the resonant modes. Okay, how do they look like? Okay, how are they distributed in phase space or in space? For this normally hyperbolic trap set, people have also found more precise description of the resonances. Okay, not only is there a gap, but there are extra gaps, and one can show along, assuming some pinching conditions on the curvature, one can find also some extra gaps, and the fact that the resonances are living in strips, in parallel strips here. And well, this requires a finer analysis, which was not done in full generality. It was done for specific systems, but not in full generality. And finally, I want to mention also a recent work by Fortsuji along these lines, which do not assume anymore the Anosov flow to be contact. And in this case, the trap set is manifold, but not a smooth manifold. It's a rough manifold. Nevertheless, they managed to find some interesting results on the distribution of resonances in this rougher setting as well. Okay, so thank you for your attention. Okay.
Any question? Question? I have a short question. In the estimate that you have for the Schrödinger equation, that you gain 1/2 minus epsilon derivatives, is that optimal? Do you lose?
Yes, I think you have to lose an epsilon. Okay, you cannot. I think you have to lose some epsilon, because otherwise, if you don't have trapping, then you can have h1/2. But I think once you have trapping, even by a single orbit, I think that you lose an epsilon. Okay, with my remembrance. Okay.
Any other question? Okay, let's send the speaker again for the talk.